Hello, everyone. So I'm Nicolas Morales. I work at Sandia National Labs, part of the Kokkos team. And today I'm going to be talking about how we can use new additions to the C++ standard, stood mdspan, for interoperability in HPC applications. So just a brief overview of what I'm going to talk about. For those of you who are not familiar with stood mdspan, I'm going to be talking about that and how it can be a powerful representation for multidimensional data. And then I'm going to talk about how we can use this for interoperability both between different HPC libraries and then also different programming languages, which is very exciting. Just as a sneak peek, I have one slide with Fortran on it. Ooh. All right, what is mdspan? So in the words of my good friend and someone who helped me with this presentation, Jakob, is the goat of multidimensional array views. So what do I mean when I say a multidimensional array views? Well, the multidimensional part is easy. A view, on the other hand, is something that is a non-owning data structure. So it essentially, you can think of it as having a pointer that points to some area of memory, and you can copy this in a very lightweight manner without having to incur the cost of copying large data structures. So mdspan was introduced in C++ 23. So it's a couple of years old at this point. You can access any of the data inside of mdspan, as you might expect. This example here, there's using the bracket operator with 3 different coordinates in this case. And what's kind of nice also in C++ 23 is you can actually do this. You could not use multiple parameters to the bracket operator in C++ 20 before then. All right, so I have a little example there. I'll kind of go in more detail about the different parts of the mdspan. So there's 4 template parameters for mdspan, and they're the way that you configure the customizability of the mdspan and how you want to represent your data. So the first one is pretty easy. It's the element type. Then we have the extents, which is the multidimensional space that mdspan covers. Then we have the layout, which is how data is laid out in memory, and then the access to policy, how you access the data. So just to put it simply, like when I go through the next slides, just kind of keep this breakdown in mind. So the idea, whenever you're accessing an element in an mdspan, you're essentially doing this operation. You're taking the accessor, and you're calling its access function with some data handle, and the offset of the data handle is applying the mapping from the layout policy with indices that are bound by the extents. So the element type is pretty straightforward. It's just whatever you want to store inside of your array data. It just has to be complete and not abstract. It can't be another array. And so here we have an example of, you have some mdspan that stores a double. I'll talk a little bit more about the second parameter, the extents, in the next slide. But essentially, you can just take some elements of that mdspan and assign doubles to them. Pretty straightforward. So the next part is the extents. So the extents basically represent how the mdspan, like what extents it actually covers. So what is the range of the indices? The first part of this is the index type. That's just pretty straightforward. It just tells you, what you're actually using, like what are the XYZ, what are the type of XYZ in that example there. The extents, on the other hand, is the parameter pack. The size, the number of elements in this parameter pack is the rank of your extents. And each one of these can either be a value specifying a static size, or it can be a dynamic extent, which means that it is the value that you're going to specify at runtime. We also provide some convenience classes for fully dynamic extents called dextents and dims. So here are some examples. Like the first one here, we just specify 3 static extents. These are ones that are determined at compile time. The second example, we have a mixture of static and dynamic. The third example, we just have dynamic extents, and then we even have the shortcuts for dextents and stood dims, which is an even shorter way of specifying fully dynamic extents. You can see we also, whenever we construct these extents, we have to pass in the runtime size. So the final example there is that you actually can have a rank 0 extent. So you see there's no actual extents there, and that is perfectly fine. So why do we want the ability to mix compile time and runtime extents? Well, this provides the compiler some opportunity for optimization, but it's also very desirable in situations in which you have like a fixed dimension known at compile time. So the classic example that I want to bring up here is like you have an array of particles, of atoms, and these exist in some three-dimensional Cartesian space. So you might want to have, you have a dynamic number of these atoms, and then the second extent is going to be static with 3 values because you're, let's say, having 3 different coordinates there. See, the third component that I want to talk about is the layout. So the layout of the mdspan specifies how data is arranged inside of the space that it spans. And it basically provides an offset, and these offsets are relevant to whatever data handle you provide mdspan. I'm trying to say this in a very general manner because, as you'll see, there's, we might not even be talking about like memory pointers at all, depending on how you specify other parts of the mdspan. So the layout defaults to layout right, which is the most efficient access on the CPU. But we have a few different layouts there: layout left, layout right, layout stride, left padded and right padded. If you are familiar with Kokkos, these might look very similar, and that's because they were inspired by Kokkos. So layout is important because it can have a huge impact on performance. So for example, if you're writing code that's running on the CPU, you generally want to use layout right because it's better caching performance. But on the GPU, you want to take advantage of the performance gains from coalescing. You would like to use layout left. So the final component of the mdspan is the accessor. So the accessor specifies how, whenever you're trying to access an element inside of the mdspan, how that is actually done. So it defaults to, well, this is the default accessor. So most of the time you don't have to worry about it, but this really gives a lot of power if you're trying to do something particularly interesting with the mdspan. So part of this, it has a few different type aliases inside of it, and then a couple of different functions that are useful to customize. So one of them is the data handle type. So this is what's actually going to be, well, if you're using a default accessor, it's going to be the pointer to your data buffer. But this could be something a little bit fancier. So it could maybe be a reference counted pointer. It could be a handle to a network socket. It could even be a file descriptor. So this is something that can really bring out some of the power here, because now if you have something like a file descriptor, whenever you can change your access function so that whenever you're accessing an element, maybe instead of accessing a bit of memory, it's actually going to be reading from disk and maybe even caching those results. So with custom accessors, you can really express a lot of different usage scenarios here. So I'm going to give some examples of how you can use custom accessors and layouts for doing some very clever things. So I also want to thank Mark Homan, who gave me some of these suggestions and who also was one of the main architects behind the Stood Linear Algebra library. So Stood Linear Algebra is a new addition in C++26, and it comes with a few different custom layouts and accessors that allow some lazy operations on matrix types, which are mdspans. So for example, there's a transpose layout, which the idea is that if you create a transpose layout, you're not actually performing any transpose operation up front, so you don't have to pay the cost of copying every element of your matrix. But whenever you access any of the elements, it's actually mapped to the transpose of that element. So you kind of get this nice lazy behavior where you only pay the cost of the transformation whenever you're accessing an element. And similarly, there's a scaling accessor and a conjugate accessor that whenever you access one of the elements will perform like a scaling or a conjugate operation on that element. You can also think about some things like if you have like non-memory access for your mdspan, like let's say, for example, you have some array that is too large to fit into memory on your node. So you could construct some cached access with that reads from disk with a custom accessor. Or you could do something like a gas type array, like where you access elements that are maybe present on other nodes, and then whenever you access them, it does a network call. So a lot of interesting things there. You can also, with the accessor, maybe change the reference type for usability. Let's say you're trying to store an image, and you're going to do some image processing on it. Maybe you're going to store it as a mdspan of bytes. But when you actually access one of the elements, maybe you want to access one of the components, like a RGB component, or maybe you want to decompress a block in the if it's like a compressed texture or something like that. So you can do that with a custom accessor. And then finally, one of the things that we've done ourselves in the Kokkos team is that we've used a new custom data handle that does our reference counting, so that whenever you copy one of our views, which uses mdspan underneath, then it will also perform the reference counting. So with that a brief introduction to mdspan, I'm going to start talking about how we can use the power of this for interoperability between libraries. So, as I've just given some examples of, mdspan can be a very powerful tool for representing multidimensional data, how it's laid out and how it's accessed. And so what's kind of interesting about this is you can, this means that the representation of your data can be done independently of the algorithm used to access it. Which, parts of the mdspan can also give indications of how best an algorithm should be able to do certain operations. For example, like the layouts that I mentioned before. But also there are other properties, such as whether a mdspan is laid out contiguously in memory and so on. So if you think about maybe a copy operation between mdspans, then if your mdspan is contiguous, you could just implement this with a simple memcopy and do something more sophisticated if elements are not contiguous in memory. So I've given hints about this before, but on Kokkos, we actually have rebased the main data structure, the Kokkos view on mdspan. If you're not familiar with Kokkos, it's a performance portable parallel programming model. And please come to our user group meeting. That's going to be tomorrow and Friday. So yeah, we recently refactored our main data structure and rebased it on mdspan. And the reason we did this, partly it was for maintenance reasons, just because if we are referring to a standard, it's going to be much easier for people to understand and update the data structure as time goes on. But another large part of it was interoperability. So the idea is that if there's any library that uses mdspan in its interface, you can now use Kokkos views with that library. So, well, what is one of those libraries? Well, I already mentioned in C++26, there's the standard linear algebra is being introduced inside of the C++ standard. And its API is completely based on mdspan. So what this really means is that if we can take one of the functions from linear algebra, I'm just using this transposed function here just for the sake of simplicity, but really linear algebra supports a bunch of different BLAS 1 and 2 operations. And this transposed function just takes an mdspan here with sort of arbitrary element type extends layout and accessor. And so if we take a Kokkos view here, that's like a 4x4 matrix, we can just simply call stdlinalg untransposed with this. We do have to convert our view to mdspan because view is not exactly mdspan, it just uses mdspan, but this operation is basically free. And so this is really interesting because it means that you can now perform linear algebra operations on Kokkos views using stdlinalg, and this is without Kokkos knowing anything about stdlinalg and without stdlinalg knowing anything about Kokkos. So it kind of creates this bridge in between. So I do have a little asterisk there, and this is just because this is just kind of assuming everything is on the host. The standard library doesn't know anything about GPUs. But our hope is that in the future, maybe some toolkits or things like NVHPC will provide a version of linalg that works with GPU views. And I'll talk a little bit more about that in my concluding remarks. So if you're planning on writing an API that uses mdspan, how should you do this? So in general, if there's any kind of any of these template parameters that you don't really care what they are, like for example element type, you should go ahead and template them like I have here in the first example. So here we have element type, layout, and accessor. This myfunc doesn't really care what they are, but it does want specifically a extent that is stood dims of 2. You can also do things like constrain some of the types. So this is if you're not familiar with the syntax, so we have requirements clauses and concepts that were introduced in C++20. So here you have the same myfunc, but this time we only allow you to call it with integral types. So this allows you to essentially exclude some things from the overload sets whenever you're calling the function, and can be useful for also querying whether an operation is possible on a particular function. Now, if you want to really you can also introduce mandates, which are essentially things that will fail at compile time if they are not satisfied. So in the case of linear algebra, as you can imagine, that library operates mostly on matrices. So you need a rank 2 mdspan. So all of those operations will actually call a static assert with that the rank of the extents is 2. All right. So now I'm going to talk a little bit about, now that we've talked about library interop, I'm going to talk about languages. And so what's the motivation behind here? So popular languages in scientific computing will often read and write process array data, for example, Fortran or Python. Python in particular is quite interesting because of the surge of support behind machine learning APIs. So if we can create some sort of translation layer from C++ to other language data constructs, we can make it easier to interoperate and talk between languages. So the idea here is that this will also improve maintainability, because if there's just like one layer for talking between C++ and Python, then you don't have to like always write your own wrappers for your own data structures. So that's kind of the idea behind all of this. So first I'll talk a little bit about Fortran. So the status quo behind Fortran interop with C++ is that there's just C-based interoperability. Since C++ is more or less compatible with C, this kind of works out. This is only the case, I believe, since Fortran 2003. And there's some caveats. And one of kind of the interesting things that you may run into if you're dealing with multidimensional data is that Fortran always views multidimensional data as column major, and C and C++ view it as row major. So if you're doing interoperability, you have to keep this in mind, and it's easy to make mistakes. Interestingly enough, mdspan, as you saw earlier, does support column major layouts. And not only that, but this is, of course, like associated with the type. It is, if you have a layout left, then that's sort of embedded in the mdspan type. So this can be easily expressed and checked with mdspan. So I actually wrote an example that showed how we could do interoperability between Fortran and C++ with mdspan. So here's some Fortran subroutine. Please forgive me, I am a complete novice to Fortran. I literally just learned it for this talk. So if there's any mistakes, you can yell at me later. But we just have this function that, as a subroutine, that prints a matrix. It takes the size of the matrix in 2 dimensions, and then it takes the actual matrix A. And this is exposed to C using the bind C construct. So on the C++ side, we have to, of course, define our extern C block, and then the signature that is supposed to match the Fortran side here. And then we have, underneath it, we have our main function. And I've created this adapter. It's called ArrayFunc adapter. I'm not going to go into the details of how it's implemented, but it is on the back of the slide if you're curious after the talk. And simply what we do here is we construct this ArrayFunc adapter with the pointer to our extern C function. then we can even, so this will automatically deduce the template parameters for kind of the mdspan type that is associated with that function signature. And so you can obtain that mdspan type. You can construct your mdspan, point it to your array data, and just call the adapter with that. And this will actually print out the matrix with the right layout. It'll be column major, and everything will work as you would hope. Similarly, you can see how we can do a similar thing with Python. And Python in particular is an excellent candidate for interop. Many high-level scientific packages use Python, such as SciPy, NumPy. Also, of course, there's the elephant in the room, which is machine learning. And Python sort of has a few different ways you can imagine doing this kind of interop. The simplest one is the native buffer protocol. So this is just built-in CPython array interop. Think of it essentially as a pointer and a size. So not nearly as complex as mdspan stuff that we've been talking about. And it works with things like byte array and array.array. But there's also some efforts to standardize some data change of more complex multidimensional array data. So there's this thing called DLPack, and it's part of this thing called the Python Array API standard. You can find more information at that link. But it is supported by things like NumPy, JAX, PyTorch, and so on. And it's worth noting with both of these is that they are actually subsets of mdspan capabilities. So we can essentially represent any of these things just with mdspan. So the next part, I want to thank Jakob for contributing this. So he wrote this wrapper for mdspan Python interoperability. And again, I'm just going to keep the full implementation on the backup slides, but this shows the usage. So on the left, you have the Python function just called process array. It's using NumPy. It's doing some things with NumPy, just assigning a value. But on the right, we have our Python bindings in C++. We're using PyBind 11. And similarly here, you're creating an mdspan of your data. And then you're doing this, boilerplate to actually find the function instead of Python, and then passing it your mdspan, but you're using this type called mdspan wrapper. And it's as simple as that. What will happen is process array will actually get the correct mdspan data and update your array and work just as expected. Okay, so I'm starting to wrap up the talk. I do want to talk about some future challenges because there's sort of also the elephant in the room about GPUs. So C++ as a standard does not know about GPUs. Some code is compatible in the standard library with GPUs, some is not. Weirdly enough, it seems to be whether or not it's context expert. It's just how most of the GPU compilers work. But I will point out that with regards to mdspan is that as the Kokkos project actually ships its own implementation of mdspan. This would be used sort of as a proof of concept when we pushed for it in the side of the standard. And our version of mdspan is device compatible. And also because we rebased Kokkos on top of mdspan, we also provide custom accessors and data handles that are associated with the memory spaces in Kokkos, like whether it's on the host or on the device. And so, maybe this could be a good roadmap for like how GPU-based mdspans could be represented for like interoperability between libraries. But the fact of the matter is that basically if we want to work with device pointers and device data, we have to come to some agreement on how to represent that using mdspans. All right. So I hope from this talk that you got the idea that mdspan is a very important tool for facilitating array data interoperability between libraries and languages. And I also do want to close with some remarks of like what this could imply for the future. I do think that this can push towards more cross-disciplinary applications. If it's much easier to communicate like array data with something like PyTorch, because of this, you could have closer integration between scientific codes with Python machine learning frameworks. I also think that it will lead to more multi-language projects and code bases. If it's easier to transfer data between languages, then the barrier to adopting maybe like another language inside of your code base that's more suited to certain tasks is much smaller. And then finally, I think that I haven't really touched too much about this at all, but I think this is also very interesting for ensemble applications. So you're running multiple smaller applications in a single allocation. And maybe you can even imagine how something like mdspan data could be serialized to a common interchange format like HDF5 and for communicating between applications. All right, thank you. And if there are any questions, I'd be happy to hear them.
Let me make one initial comment, and that's on me that I didn't even review your slides before, you sent me, and I didn't get to it. But one thing to say is that the mdspan implementation, when you said, we have our mdspan implementation, yes, it's in the Kokkos ecosystem, but it doesn't depend on anything else in Kokkos, right? So you can use that mdspan backport to C++17 and C++20, which is GPU compatible without depending on anything else in Kokkos, right? There is not even the Kokkos function macros or anything like that flying around.
Yeah, and you can even, with some things, use it in 14, but try and get at least 17 for that.
Does mdspan support slice?
Yes, so I didn't really touch about sub-mdspan at all. Sub-mdspan is essentially a way of providing slice operations on the mdspan. And that's one of the main ways you can get non-contiguous views, for example.
Okay.
Or
my second question is perhaps a little bit out there. Can you go back to your Fortran bind C? Okay. I find all of this super annoying to go from Fortran to C to C++. Mm-hmm. Is there any appetite for doing direct Fortran to C++, so you don't have to go through C and do all of this type nonsense?
Yeah, I mean, that would be really nice. I'm not really in tune with the Fortran standard. It would be cool if they provided ways of doing that. But yeah, I kind of just learned Fortran just for this talk, so yeah, I'm not really in tune with what they're talking about there.
Hey, great presentation, great work. Since we talk about Fortran, let's stay there. One question I have is, and seriously though, both in Fortran but also in wrappers that we use in distributed libraries, we usually have support for good reasons to have non-zero based indexing. Mm-hmm. So. Thank you. So the question is, I think it's, how would you implement this? On top of mdspan and carry the metadata around? Or is this actually possible to express in mdspan intentionally, cleverly with the current templates we have? Yeah.
Yeah, so, I think you could, well, okay, I'll say that, so mdspan is very much zero-based. But the thing is that I don't know how much the one-based index would matter here, because I understand on the Fortran side everything will be one-based, but you're
or negative, yeah, it's actually if you think of a MPI distributed array of 10,000 entries, mm-hmm. you want it's really cool to have on processor 17 200 to 400 or something mm-hmm. like this, or negative for guard cells, stuff like this. Yeah.
Yeah, so you could probably do something fancy with a custom layout in order to do that. I will say that probably on the C++ side of things, you're going to still stick to sort of a zero-based index. But the idea here is even if you're using one-based indexing on the Fortran side, and zero-based indexing on the C++ side, it's just your indices might be will be off by one, right? But ideally you'd be doing different operations on either side, I guess.
Yeah. So okay. Yeah, I would be interested just if we could give community guidance for this on mdspan, because I think it is really one argument that really Fortran programmers will look at, and then what people have to implement anyway in distributed libraries. So it would be great if we either build an object generally on top of that, or show how we can express it in a current template policy. That would just be cool for sitting down and hacking together.
Yeah, sounds good.
You can't make a layout which does one-based indexing that just doesn't work in the standard way it's defined. But you can inherit from mdspan. So you make your 1D, one-based mdspan, inherit from it, and just add +1 to every end, or -1 to everything, right? So that's the way to go. And maybe, one thing we can do is we could, in the if there is appetite for that in this community, right, and there's people who are interested in, coming together for more interoperability, we could implement that in the, in that mdspan repository, right? We could have extensions there, like the HPSF standard set of extensions, for example, for accessors which do the GPU awareness, for things like the Fortran interoperability, 1D based, one-based array, right, and other things like that. We make it very clear. Here's the standard set, here's the extension set, and if we all do that together in one place instead of everybody re-implementing the same thing, maybe that's the way to go, right? That's what we're all here for.
Yes, thanks for that comment, Christian. Yeah, it's very much kind of like what we're trying to do with this is create kind of like a community understanding of this kind of interoperability. So yeah. All right, if there are no more questions, thank you very much, and I release you all to lunch.